All right, howdy. My name's Reed.
My name is Eugenio.
And Ricardo.
My name is Daniel.
We're going to be talking about our MXET 300 Mechatronics final project. And in this project, we decided we wanted to make an autonomous CQB battle robot. So here are some of our project links. So on the top, we have the YouTube video with our demo. We'll be uploading this presentation afterwards. Then below, we have our Google Drive with all of our folders and our codes, and our GitHub's also in our code's also in our GitHub.
So here, the goal was to design an autonomous close-quarter combat robot that cleared out rooms, detected if targets were friendly or hostile, and shot ping pong balls at targets. So here what you can see in the video is it's going to detect the doorway. Once it detects the doorway, it's going to engage the room. Once it's actually engaging the room, it's going to see if the target is friendly or hostile, and then that will decide whether it shoots or not. And after it's shot or not, it will go back into the hallway and continue navigation. And so here you can see the same thing, but it actually goes into a right turn instead of a left turn from the previous video. And so here for the LiDAR, the code was divided into 6 states determined by the LiDAR reading. So we had navigate, pause for obstacle, turn to door, engage room, return to hallway, and end of hall. Our robot constantly read the LiDAR, centered itself between the hallway doors, and looked for sudden openings that indicated a doorway. Once it actually detected a doorway, it drove forward a little bit and then turned 90 degrees into the room, stopped, and ran the color tracking shooter code. Then it turned 90 degrees back and continued down the hallway. I also added some safeguards, so if anything was blocking the front, it would pause until the path was cleared, and then once it actually reached the end of the hall, it would stop moving completely.
So yeah, for the color tracking code, we decided in order to distinguish between the hostile and the friendly targets, we thought it would be best to use the camera to differentiate between the red and green. So to do so, we had to use the computer vision. So in our code, we made it very similar to the code used in Lab 8, except we found that the challenge was we had to distinguish between two distinct colors this time instead of one. So we figured the best way to do this was to create two individual variables and then use a logic OR gate. So we'll constantly be looking for red or green. So if it was red, it'll drive up to it, get itself within 150 pixels, and then shoot. But if it's green, it'll only drive up to the 150 pixels and then stop. Then Ricky will talk about how it shoots.
So for the shooter code, we used two different motors, and it was mainly for the flywheel. We used the H-bridge motor controller using the GPIO pins. And what we did was we used ones and zeros to go from full ramp up at 1 to full stop at 0. Once it detected a object to target, could have been red, it shot, and green, it didn't shoot. We also implemented the servo code here for the servo logic, which is sort of the same as using zeros. And no, it was using ones and -1 for the position as full 90 degrees at 1 and going retracting at -1. That's how the shooter logic worked. And an important thing to note here was that we had to use common grounds for the motors in the flywheel in order for them to work simultaneously with the H bridge.
Yeah, for like the hardware side of the shooter mechanism, you can see the CAD model that we printed out here is mounted onto the robot. We elevated it up so that it's above the LiDAR so it doesn't interfere with the detection system and the hallway path follow. We mounted both batteries on the side because we needed enough battery to run both four wheels and also the LiDAR and the Pi. And so basically, the two flywheels are up there, and there's a servo trigger. If you see in the bottom right image, when it goes in the forward position, it holds up the other balls that are loaded up, and it'll return back to drop and load a ball, and then it'll shoot it forward whenever it's ready to shoot a red target. And we mounted the LiDAR in the front just so that it has the most vision, as well as the camera so that it detects the target if it's hostile or friendly. Now for the 3D modeling, we decided to go with the design. And over here on the right side, you can see like the ball loader and it's able to hold up to like three balls. And the servo trigger, you can see on the top side how it's able to hold up the rest of the balls. And for the extended barrel, this was like a third iteration we did because first of all, we tried to just do like with the stock driving motors with the gear with the wheels, and it was not shooting fast enough. So we redesigned the motor gear and the wheel gear so that it goes from a big ratio to a small ratio, and it'll speed it up. And it did help, but it still didn't shoot as fast as we would have liked it to. So we added the barrel so that it goes past the camera and the LiDAR and actually hits the target, as you can see in the video.
You're muted, Ricky.
So right here for the system overview, you can see how our Raspberry Pi is pretty much the center or the brain of our whole operation. You can see the red cables being power and voltage, black being grounds, yellows being control and signal, and the grays being sensor feedback. Like for example, LiDAR camera and the IMUs and encoders are connected through a gray cable as a sensor. And then we could also see how our battery packs share common ground between the motor controllers and all the motors. And for the system overview, also we see how our scuttle should operate, where it goes with the LiDAR and finds an opening door. It locates a target, which in this case the first target is red. We'll turn and shoot how we saw in the video, and it goes back and keeps searching. And if it sees a green target, it won't shoot and keep performing the tasks it was assigned.
All right, so now for the effort distribution technical work, start off with what I did. I worked on the CAD modeling for the shooting mechanism for the gear, new gears and stuff like that. And then as well as I helped out with the gap detection with the LiDAR code.
I was responsible for the obstacle avoidance, gap detection, and centering LiDAR code, and then I also worked with the shooting mechanism code.
I was responsible for the target detection and shooter code, and also combining the system implementation of the LiDAR and shooter code.
Now I was responsible for the color tracking code, as well as implementation and assembly of the full robot. And finally, I'll go over the timeline quickly. So in the first week, all we did was brainstorm and order components, which is the servo. That's where we decided we want to work on the CQB and began designing. In week 2, this is where we began working on our actual software. This was the target detection and the shooting mechanism. This was also where we began to 3D CAD and 3D model. Then week 3, we had about all of our parts assembled. This is where the testing and the real grind started, where we had to do a lot of testing and make adjustments as needed. And finally, this week, we finished up with our final project presentation. All right, so yeah, thank you all.